Neptune, the eighth and most distant planet from the Sun, has long been seen as a quiet, lonely giant, an icy blue marble drifting in the darkness. For years, we imagined Neptune as a world of stillness, wrapped in calm, far from the chaos of the inner solar system, but recent discoveries have shattered that image. New evidence from our most advanced telescopes reveals Neptune as a stage for violent, energetic events, far from the frozen slumber we once believed. This isn't just a minor update, it's a paradigm shift in how we see this distant world. Neptune is no longer a static sentinel but a planet with a vibrant, active inner life, shaped by forces we're only beginning to understand. The story of this discovery is a testament to human curiosity, peeling back the layers of Neptune's blue facade to reveal a world alive with cosmic drama. To grasp the magnitude of Neptune's transformation, we must first appreciate its remoteness, over 4.5 billion kilometers from the Sun, 30 times farther than Earth. Sunlight here is faint, and the cold is extreme, making Neptune one of the most mysterious planets in our solar system. Our first close-up came in 1989 when Voyager 2 revealed a stunning blue world, faint rings and new moons, and a massive storm called the Great Dark Spot. But that flyby was brief, leaving us with more questions than answers. For decades, only blurry images from distant telescopes hinted at Neptune's secrets. We knew about its frigid temperatures and supersonic winds, but the planet's true nature remained elusive. How did Neptune form so far from the Sun? Why does it emit more heat than it receives? These questions made Neptune a tantalizing mystery. It was a cold case, waiting for a new detective and new technology to crack it open. Enter the James Webb Space Telescope, a revolutionary eye on the universe, launched in 2021. Unlike Hubble, Webb sees in infrared, allowing it to peer through cosmic dust and detect the faint heat of distant worlds like Neptune. Its massive gold-coated mirror and million-mile vantage point give it unmatched sensitivity. Webb's instruments, especially NIRCam and NIRSpec, can capture sharp images and break down light into chemical fingerprints. When astronomers turned Webb toward Neptune, they could finally dissect its atmosphere, study its rings, and map its storms with unprecedented detail. The stage was set for a new era of Neptunian exploration. Old questions awaited answers, but the universe had a new surprise in store. Webb's capabilities promised not just clearer images but a deeper understanding of Neptune's hidden dynamics. The quiet giant was about to reveal its secrets. Webb's first images of Neptune were breathtaking. Its rings glowed, moons sparkled, and high-altitude clouds streaked across the planet. But then scientists noticed something extraordinary. A powerful, concentrated glow near one of Neptune's poles. This wasn't a storm or a cloud, but a sudden, intense heating event in the upper atmosphere. The initial theory was dramatic. Had something struck Neptune? But as the data came in, it became clear. This was no impact, but a flare of energy from a different source. Neptune's calm exterior was hiding a spectacular cosmic light show. The bright glow wasn't caused by a collision with a space rock, but by a surge of energy from the solar wind. A stream of charged particles from the Sun. When these particles hit Neptune's magnetic field, they're funneled toward the poles, colliding with atmospheric gases and creating a massive aurora. This is the same process that creates the northern and southern lights on Earth, but on Neptune it's far more powerful. Webb's data showed the heating of Neptune's upper atmosphere, not debris from an impact. The result, a shimmering infrared curtain of light, proof that Neptune is intimately connected to the Sun, even at its vast distance. The quiet giant is constantly battling a storm of solar particles. Neptune's auroras are a reminder that no planet is truly isolated from the Sun's reach. The discovery redefines Neptune as an active participant in the solar system's cosmic weather. To confirm the aurora, scientists needed a chemical fingerprint, something only an aurora could produce. Webb's spectrograph found it trihydrogen, or H3+, a molecule formed when solar wind particles energize Neptune's atmosphere. H3+ glows in infrared, acting as both a signature of auroral activity and a natural thermometer. This was the first detection of H3+ on Neptune, irrefutable proof of the aurora. By tracking H3+ emissions, scientists can now monitor Neptune's space weather in real time. They can watch auroras brighten and fade with the solar wind, revealing the planet's dynamic relationship with the Sun. This discovery opens a new window into Neptune's climate and chemistry. The ice giant's upper atmosphere is now a laboratory for studying energy and magnetism on a grand scale. Neptune's auroras are not just beautiful, they're a key to understanding planetary atmospheres across the galaxy. Neptune's aurora wasn't at the pole, but closer to the planet's midsection. a clue to its bizarre magnetic field. Unlike Earth, Neptune's magnetic field is tilted by 47 degrees and offset from the planet's center, causing its magnetosphere to wobble wildly. This means auroras can appear far from the poles, tracing the strange paths of Neptune's magnetic field lines. Webb's observation of a mid-latitude aurora confirms this chaotic magnetic geometry, first hinted at by Voyager 2. Understanding Neptune's magnetic field helps us interpret ice giants across the galaxy, many of which may have similar quirks. Neptune is now a dynamic laboratory for planetary science, showing us how magnetic fields, solar wind, and atmospheres interact. As Webb continues its mission, Neptune's secrets will help us unlock the mysteries of distant worlds. The once quiet giant is now a beacon of discovery, reshaping our view of the solar system. The cosmic ocean is full of surprises, and Neptune is just the beginning.